Yes, it started. Okay, good. So first of all, these three variables, theta, beta, and phi, in your geometry books, I taught you teach geometry here, but I didn't use the book that you guys are using now. I used the book before that one. You used x, y, and z, right, for angle variables, unknown angles in your geometry problems, right? Okay. Well, when I taught geometry here for a while, for our physics, we used these Greek symbols. Okay, these are the symbols just as they appear on like a fraternity or a sorority house, above the front door. So theta is just a circle with like a tilde or a squiggle in it. So if there's only one angle floating around in a problem, it's typical that someone in science starts with theta. You'll find these angles are in your book when we get to some problems with angles. If you have a second angle in the same problem, you don't use theta again, you go to like beta, right? And then if you have a third angle, which is rare, but if you have a third angle that you don't know and you need to find, they'll use phi. Got it? Okay. Now I'm going to talk about how they present, or they give you vectors. The first example is going to be, they can give you a word description of a vector, and then you create the drawing for the vector, all right? For instance, so this would be ways. Vectors are, you know what I mean by given, right? Ways that are communicated to you in a problem, such as their magnitude, right? The length of the vector arrow and the direction. So let's say that words, okay? Words are used. So let's say that Becky walks 23 meters at 32 degrees south of east. That is a very common way for a vector to be communicated to you. In this case, it's a displacement vector, right? So what happens is, you need to make a diagram now. We're going to use the cardinal direction system, all right? The cardinal direction system. That means we're going to use north, south, east, and west. That is the cardinal direction system. There's another direction system called the bearing, and that is where they use 0 to 360 degrees like on a compass, and that is used for navigation, such as airplanes and ships, primarily. So this is a top-down view. Now we want to place a vector in the proper location for which way she walks. So let's talk about this south of east beeswax here. See that? The way we know the length of the vector is going to be 23 meters. Okay? And it's going to be in this general vicinity. Here's how this works. You're always coming off or starting, so point your finger or point whatever is representing the vector. You point it in the direction of the second word, so east. So these two words will always be one of these four directions. They could be north, south, east, west. It could be positive y, negative y, right? Positive x, negative x. Those are the typical ones. So now you go 32 degrees south, away from east. So you rotate away from east, and you head towards south until you get 32 degrees. So this is 32 degrees south. You can also exchange this word of with the word from if you want to. They write of, but from. So 32 degrees from east. So tell me when to stop. You didn't tell me when to stop. You got to tell me when to stop. I want 32 degrees between east and this ruler. Okay, you didn't tell me. I mean, I'm at 90 degrees. So okay, tell me when to stop when it's 32. Come on. Yeah, thank you. All right, so 32. Let's draw that in. Okay. So approximately, it's a freehand diagram. So yeah, so it's 32 degrees, right? And this is 23 meters long. Okay. So that's what we do with that. Now, another way that vectors can be given to you is in a diagram. So words were given here, we created the diagram. Now, we're going to be given a diagram. The first one up here, that's a top-down view, right? The top-down view? like from a helicopter, a balloon, or like a drone. You're looking down on a map, maybe. Okay, so now we have the floor, and we're going to have a crate. Okay, so this is a crate sitting on a level floor. And typically, I'm going to use a force vector now. Okay, a force vector. So when we have a force vector, what we do is we generally connect their tails of the vectors, force vectors, to the center of the object in question. It helps us find angles. All right? So this will be the force vector. All right, and I'm going to say that this is 75 newtons in. Okay, this is a word I've mentioned before. Now we're going to talk about a little bit. Newton. That means 75 newtons of force. And I'm going to give you an angle reference here. We need an angle reference. Remember using dashed lines in geometry? Auxiliary lines in geometry sometimes, right? Extend things and whatnot. Have you done that? Yeah? Okay. So let's just say that this is 31 degrees. So I have a force pulling up on the crate at an angle of 31 degrees above horizontal. So this would be given to you, this diagram. Got it? Not words, but you're already given the diagram, right? Okay. Now, what is a Newton? Okay. This is a 1 Newton apple. It is specifically designed for this part of physics class or science class. So a Newton is the metric unit for force. A Newton is about, it's 0.2258 on your green paper. Yes, it's 0.2248 of a pound. So 0.2 is a fifth of something, right? 0.2. 0.25 is a fourth of something, right? So 0.2248 is in between a fourth and a fifth of a pound. So a Newton is between a fourth and a fifth of a pound. Got it? So it's the average. A Newton is how hard an average weight apple, average size apple, pushes down on your hand. That's approximately what a Newton is. Okay. So now let's say, and this is where we're going to pick up the vectors that we're going to start actually calculating on. Let's say that this is another way that vectors can be presented to you. All right. So that's a bit long. So let's say that we have an elephant, all right, and it's stuck in the mud, and they're pulling on it with 3 ropes. And I realize that these amounts of force are really too low for an elephant, but I want to keep the numbers reasonably small. So let's make this 5.0, so I have 2 sig figs. All right, so the elephant would be here. Okay, so here's the elephant, right? Now, the reason they're pulling in different directions, let's say the elephant's stuck in the mud, and there's a lot of mud around the elephant, but the people found some spots where the dirt wasn't too muddy and they could get some traction. So they're standing here and there and there. Now, these do not represent the lengths of the rope. These vectors represent how hard each rope is being pulled, right? It's the force in the rope. So this person is either weak or can't get a really good footing. This person's able to apply more force, and this person is pulling with the most force. This does not indicate the length of the ropes. The length of the arrows represents the strength of the force, right? Okay. Now we're going to provide some angles in here. Okay. So this would be like the diagram that you're given, and this would we've been using 37 degrees up here, 37 degrees up there, and 41 degrees down here. Okay? So those are the vectors that we're going to use. Now I'm going to come over to the other side. Don't get dizzy if you're watching this video. Sorry. There we go. Okay. So here we go. We are going to figure out how to add those 3 vectors that we just drew. Okay. So we're going to separate them. All right, so we're going to take the 5 Newton vector, 5.0 newtons. It's going to go up, and then we're going to take the 10 Newton vector, and it's going to go this way, 10 newtons, and then we have a 37-degree angle, correct? 37-degree angle. That's a bad 3. And then the other vector that we have to add together with these two is a 14 Newton vector, and that is at an angle of 41 degrees. Now, the hardest thing you've got to do today is use sine, cosine, or tangent, all right? And I'm actually going to, at one point, I'm going to explain that you can basically use cosine twice and skip sine if you can't keep it straight. So here's what happens. Any vectors that are on what I call the tilt, meaning they're not perfectly straight up or straight down, they're not vertical, or they're not horizontal. So if they're somewhere pointing at some angle in one of the 4 quadrants, right, we have to do this process that we're going to do on these two, but we don't have to do it on the 5 Newton vector because it's already pointing up, okay? So we would say the 5 Newton vector does not have a horizontal component, but these two do. So I'm going to color code my directions here. First of all, I'm going to walk you through the whole right triangle concept, okay? So this will be 10. So I'm going to leave the arrows off, and I just want you to think about a right triangle, okay? That's not very level. There we go. Then we're going to come down here, okay? So all my vertical components, I'm going to go with green. All my horizontal components, I'm going to use blue. So let's transfer the 37-degree angle into here, okay? So I know everybody in this room has had the math in the geometry class, the right triangle math. You should be able to find the lengths of those two unknown legs, correct? So let's review that. So we're going to use SOHCAHTOA, all right? I'll write SOHCAHTOA right here so it'll fit in the camera. So we're going to be using SOHCAHTOA, okay? Now actually, I'm going to move the camera over here so I can develop this out. Okay, so camera has to come over here for a minute. I'll develop this out. Okay, we've got SOHCAHTOA. SOHCAHTOA, right? Now, what is the first thing is the SO is what? Sine theta equals what over what? Opposite over the hypotenuse. Everybody knows that. But I want you to rework that, and I want it to be opposite equals. So what will that be? Hypotenuse times sine theta. That's the way I like to write it. Do we agree on that? Everybody good? Okay. So if we're using the 37-degree angle, let me come back over here. Okay. If we're using the 37-degree angle, oh, it'll all fit. Good. We're using this 37-degree angle here. What does that make the green side? Hypotenuse, opposite, or adjacent? Opposite, okay. So this will be opposite, in this particular diagram, is the hypotenuse times the sine of theta, correct? Well, we know the length of the hypotenuse is 10. I don't necessarily write the units here. I just use the numbers, process the numbers, and the sine of 37 degrees. Is that correct? Now let's crank that out, and what do you get? Use your calculator. What do you get on the display? By the way, you need to make sure that your calculator is in degree mode. Calculator in degree mode, not radians, okay? Or it won't work. So who's got a number for us? I've got 6.018. Does anybody have 6.018? You get 6.018?
Yeah.
Okay. All right. We want to round that to 2 sig figs. Why? Because the angle is 2 sig figs, and I'll just put a dot behind the 10. That makes that now based on your chemistry. So what is it at 6 point, how much is that then? What is 6.08 rounded to 2 sig figs? 6.0, right? Okay. So that's where we're using those rounding rules. We have 2 sig figs times a 2 sig fig number. Okay, so this is 6.0. Okay, on the opposite side. Now, let's go through and do the same thing for, so what is it for cosine? What's cosine? Cosine is what over what? Oops, cosine theta, again, unknown angle, is adjacent side over the hypotenuse, right? Can't make that out on the screen, so I'm going to do something darker here. It is cosine theta equals adjacent side over the hypotenuse. But again, now what do I want to rework this into? I want adjacent, right? What does that equal? Hypotenuse times the cosine of theta. Is that right? Is that right? Okay. So now let's process this side. Okay, so this is going to be ADJ. This is do you agree that's the adjacent side? Put your finger on the angle, right? And the adjacent side is the neighbor. It's next to the angle, right? Okay. This is the opposite side from my finger, where the angle's at. So this is the hypotenuse times the cosine of theta. And that will be 10 times the cosine of 37 degrees. And that will be how much? Before we round, 37 cosine times 10. 7.986. 7.986, but we want that to become what? 8.0 to 2 sig figs, right? So this is 8.0. Now I want to show you where this leg and that leg fit in up here and are considered the component vectors of the original 10 Newton vector. So this one is easy. So this is the x component, and it is 8.0 newtons long, and this is the x component. Soon I'll just be writing COMP for component, save some writing. And I'm going to put, for the time being, I'm going to put the green vertical vector, and that is 6.0 newtons, and that is the y component vector. Does that make sense? Now, are we good? Everything clear so far? All right. So here's the deal. How are the green and the blue vectors connected right now? Are they connected head to tail? And by the way, they'll always be perpendicular because one's horizontal, one's vertical, right? So these are the only 2 component vectors that can exist for this 10 Newton vector at that angle, above horizontal. Now, I can put them in different places, but if you connect them head to tail, it's going to look like that. Now, you can also put the blue one, it could be here, and the green one could be over here, right? Okay? It doesn't really matter where you put them. Just usually, now this is how we normally do it though. Normally, we would have them sitting here, and here. So that's normally where people put them once they get to going on this stuff. Okay, but I needed to go through the triangle process for you, right? Okay. All right. Now I'm going to show you a shortcut. Okay, but do you understand what happened? Okay, but this is the typical way. Now I'm going to show you how you can use cosine twice and be done and not have to make triangles unless you want to, unless that's your thing. Okay, so I'm going to draw. This would be the vertical component, right? How long is the vertical component? Well, imagine that you're shining a flashlight over here, right? You're shining a flashlight here, and it needs to come down just a little bit. And it will come down to a line like here. Right? Little dashed line, we're going to create a rectangle. But imagine that you're shining a flashlight this way, and they call the component vectors the projection. What it really means is the shadow. So if I shine a light, a flashlight here so that the light rays are all parallel, then this would be the shadow you would see on the y-axis. Do you agree with that? Okay. Now we want to shine the light up from the bottom, right? And what would the shadow be? This blocking the light, like if I had the ruler here, and it blocked the flashlight, how long would the shadow be on the x-axis? Can you visualize that? Tell me when to stop. Right there, okay. All right. Now I realize my 8 and my 6 are about equal in length, but that's because it's a freehand diagram, right? Okay, if somebody was doing a little better job, that 8 would be a little bit longer. 33% longer to be exact. 2 is 33% longer than 6. 2 is 33% of 6. Okay, so here's how you can, now let's use this, let's find this side. Okay, so what would I use to find this side? I'm using this angle, here's my hypotenuse of 14. Do I use sine or cosine? So the angle is touching the side I want. I'm going to use cosine. So this is the adjacent side, right, for that angle, and that's going to be 14 cosine, right? 41 degrees, is that correct? And how much will that be? 41 cosine times 14. I've got 10.57. 10.57, but again, we want to round to 2 sig figs, so how much? 11, is that right? 11 newtons. Good? And here's how you can use cosine twice if you want. If you want to use sine, just visualize that this is over here, right? The green one is over here, so now it's the opposite of 41, right? You can use sine. But what if we knew this angle? Then we could use cosine for this side too, right? What is this angle? What's this angle got to be? 49. It's got to be 49 degrees because we know that this is a right angle up here, correct? This is a right angle because we know the horizontal and vertical component vectors are perpendicular. Because one's horizontal, one's vertical. So therefore, these angles will be complementary. They both add up to 90. So you can easily find the other one, right? So now we can say this is going to be also the adjacent side, but I'm going to be using this angle, right? So that's going to be 14 cosine of 49 degrees, okay? So what is that going to be? What is 14 cosine 49 degrees? Let me write this a little better. This side is 14 times the cosine of 49 degrees, which is 9.18, right? We don't need the ADJ on there because we know if we use the angle touching the side we're finding, touching the component, you're always just going to use cosine, right? Then you don't have to worry about it if it's not a sine or cosine. Okay. So how much is this going to get rounded to? 2 sig figs. 9.18 to 2 sig figs, please. 9.2 newtons, right? Okay, good. The hard part's over, believe it or not. So this is 9.2 newtons. And the horizontal leg is 11 newtons, right? Okay. Now, I got to clean some real estate off over here to do the last part. Okay. So, did anybody want to take a picture of that or anything? No, it's going to be on the video I post. Okay, so here's what's going to happen. You ready? I'm going to erase some of this because I don't need it anymore. I'm going to dab it out. See, I'm dabbing that out. I don't need the angle, and I don't need the original vector anymore. I don't need the angles, and I don't need the original vector. I do want that 11 in there, though. I want to clearly say that that's 11 newtons, all right? So now, do you see any vectors left up there that are at an angle on the tilt? They've been replaced. The two that were on the tilt have been replaced by only vertical and horizontal component vectors, correct? Now, since vectors are either left, right, or up, down, we can easily add them. We add the apples with the apples. We add the horizontals to get one overall horizontal. And we add the verticals to the verticals to get one overall vertical. That's pretty easy, right? Because that's just adding and subtracting. So now we will add all of the, so let's add all vertical vectors to get one. There is no special name for it. I just call it the overall vertical vector. So I recommend that you put a plus sign on vectors, even though it is indicated to be positive by the up direction of the arrow. All right? And the way vectors get their signs here, I'll use a different color when I'm adding here. So this is an addition sign, and that is a direction sign. And then we have a 6 Newton one, right? A little bit longer, is that right? So plus a 6.0 Newton one. And then what do we have? Plus what? Plus a 9.2, which way does it point? Down, right? So I need to make that one longer. So that's plus a negative 9.2 newtons, is that right? Okay, so let's add all those up. So what do you get? You've got 11 plus a negative 9.2. So what is that all added up? Is that a positive or negative? So it's a positive 1.8 newtons. So which way is the vector going to point? So the overall vector is going to point up a little bit, right? Are we good with that? Now, if we wanted to, we could have connected these head to tail and seen that, right? But we need to get into a numerical mode and save time. What am I going to do next? What's next, do you think? Huh? Yeah, we added the apples together. Now we got to add the oranges together. So add all horizontal vectors to get one. How many do you see? Just 2. And they happen to both be a component of a vector that was on the tilt, right? We were not given any vectors that were purely horizontal, right? Correct? In the negative or the positive direction. And you understand we're picking up those signs from positive y, negative y direction, negative x direction, positive x direction, right? From the math? Okay. So let's add those up. So we have a what? What's the first one we're going to add? 8. So 8.0 newtons. Let's put a plus sign in front. Again, it's good to put plus and negative signs on these and not just rely on the arrows, because what will happen is you'll miss the direction. You'll not take into account that something's pointing left, and it should be a negative, and you'll treat it as a positive, or it's pointing down, and you'll think like here, this is pointing down, but if you just had 9.2 there, mentally you're supposed to make that negative, but you might not, right? Because you're looking at signs. Anyway, so what is the other one? 11, is that right? So 11 newtons, and how much is that going to give us? Okay, so that's going to give us a 19, a long vector, and it's going to be 19 newtons. Okay? Now we're at the final phase, and this is where Pythagorean theorem and inverse tangent are going to come into play. Okay? That was a very bad 19. Very bad. That is a better 19. So we are going to take this vector and this vector. This is your overall vertical vector, right? Overall horizontal vector. And we are going to add these two vectors. How do you add vectors? Head to tail, right? So I'm now going to make a diagram where I take those two vectors and I connect them head to tail. So I'll stay consistent with my color coding. So the horizontal vector is green, right? And that's going to be 19 newtons long. And the vertical vector, I'll use blue, and it's got to point which way? Up. So let's say it's right there. Now, it is actually not important to put the signs, just the direction over here. You want to put the signs at this stage, you can. All right. So here's the deal now. Do I have two vectors? By the way, how many ways can you connect two vectors? 2 factorial, right? So 2 ways. I'm just showing you one way. On the paper you have with all the steps, I show you both ways at the end, right? See that at the end? That would be step 4? See how I showed you both ways? Okay. So now we want to connect the beginning of the vector trail to the end of the vector trail. I like to use dashes for the resultant vector. And which end will the resultant vector have the arrow on it? Will it be on the right-hand side or the left-hand side? On the right-hand side. The resultant vector is the only vector that gets connected tail to tail and head to head, right? And how long will it be? It will be this long. Red's not showing up too good, but we've got a lot of glare going on here. Let's see if I can move this over just a little bit. Come on. I think I'm making him dizzy. Hold on, people. Hold on. It's not going to work. I created a problem. Sorry. Massive fail at the end here. Okay, they can't see that in the diagram, so I'm going to have to change this to black. All right, it's going to be the square root of 1.8 squared plus 19 squared, isn't it? And I believe that's the square root of, let's go ahead and process that out. I believe it's 364. 1.8 squared plus 19 squared is 364. Now that will equal, take the square root of that. That will equal 19.08. Well, it is a little longer than 19. Let's sort of block that a little bit. What's the problem? If we round that to 2 sig figs, what do we get? We get 19. And some people that bothers them, but it's the way science works. We're going to find this angle, and you're going to see how close to 90 this angle is, which means this green horizontal vector and this slightly tilted resultant vector are almost parallel to each other. And if you have two sides in a triangle that are almost parallel, that's going to indicate that they're almost the same length. So here's our final piece of the puzzle. Are you ready? We need to find this angle here. Angle, I'm going to use purple on that. angle theta here. You always find angles at where the tail of the vector in question that you're finding the direction for and the angle for, the tail is the vertex of the angle. You never find a vector at the head of the angle at the head of a vector to use it for that vector's direction. The vector itself is always one side of the angle that you're using for an angle reference, okay? Get that? So you always are finding an angle to use for a direction for a vector where the angle's vertex is the tail of the vector. So now we're going to use, excuse me. So now we're going to find theta here. So theta equals the inverse tangent. Now what is tangent? What over what? Opposite over adjacent, TOA, right? What is the opposite side in this? Excuse me. What is the opposite side? 19. Don't worry about the units. What is the adjacent side length? 1.8. Okay. Now, if you process that with your calculator, you've got inverse tangents. Now, first, just to help people that don't understand sometimes what these things do, 1.8. You just divide so this is the ratio, 19 divided by this 10.56. That represents the ratio of one leg of the triangle to the other leg of the triangle. Okay. Now I hit inverse tangent on my calculator, and I get this. So this is the angle that produces that ratio. So it's 84.59, but we want 2 sig figs, so how much? 85 degrees, right? So there is our final answer for that. Okay? And we will stop at that. So we know the length of the vector. We know the vector's magnitude is 19 newtons, right? Rounded, I understand that's the same as this, but you do agree it is, in real life, it is slightly longer, right? It has to stretch just a little bit more distance? Okay, very good. So you've seen the component method, and we'll talk later about how to use that angle and write out a proper description of a vector, okay?